pull on one object, but that object is connected by something to another object. So a train question. I think you can imagine variations on this. They're not on wheels, they're being dragged across the floor, so there's friction. The whole thing could be placed on a ramp, and now we're pulling them up a ramp. There's a lot of variations on the way we could talk about these kinds of questions, but there's still a multi-body problem, there's still a force problem, and generally we ask questions like, what is the acceleration of the system? Maybe what is the force on the coupling between the objects? So it's pretty straightforward, pretty much like what we just did. So in the problem you just did, you were asked to find the acceleration of the two boxes and the tension in the cable. In this thing, I'm going to ask the same thing. What is the acceleration of the two boxes, and what is the tension between them? And these problems start the same way as the other problems have started, by starting with a free body diagram and trying to see if you can figure out what the forces are that are acting on your system. There are shortcuts here, and you're going to see one of them pretty quickly, I think. So why don't we start by you guys drawing a free body diagram for each of the objects, and let's put some numbers to this, because I want to start with this. Some of you got tripped up in this last one because I gave you numbers to use, and you didn't know how to deal with that, with many of our examples being just M1 and M2. So let's say this is 15 kilograms and 5 kilograms, and then we'll do our next example in terms of like M1s and M2s. And now getting back to this idea that we're going to see the entire mass of the system somewhere. At the end of the day, that's what we have here. And so 10 equals 20A, or A equals 0.5 meters per second squared. That would be the acceleration of the system. Now, like I said before, we can treat it like one big box that has this mass, but we know it came from two different boxes. And there's force between them right here. So the next thing to do is to figure out, well, how much force is there between them? And we can take this back up here and put it in either one of these to figure out what the tension is. In fact, for you guys who are struggling a little bit, one of the things to consider is that if you can get the acceleration, then either one of those equations will tell you what the tension is. Try both of them. If they don't agree, if you get two different numbers, then this number has to be wrong. They have to work together. They have to give you the same answer. So always make sure you look for ways to check your work. So I'm going to do that just so that those of you who may have some struggles can see that you're going to get the same answer. So this is one way to find the answer. It's the more complicated way, but we'll do it first. 0.5 times 15 is 7.5. Add t to both sides. Subtract 7.5. That's what I would expect the tension to be. Now, at the same time, I could have put it in here. And I get t equals 5 times 0.5, and that is also 2.5. Checking my work. Well, making sure that everything works out like it's supposed to. All right, so two implications here that are different than before. First, if we look at what's happening to this car is quite literally being pulled apart. And you have to recognize that. In real life, this car is experiencing 10 newtons this way and 2.5 newtons this way. If it can't take that amount of pulling force, it will break, it'll separate. Now, that's not very much here. It's just talking about toy level sizes here. But the truth is, they put together train cars not in an accidental way. They put them in, of course, a way that is easy for them to disconnect them at their sites, but also they have to make sure they can withstand the kind of forces. Now, we put the heavier car first. Do you think it makes a difference if you put the heavier car first versus the lighter car first?
Yes.
We should try it. In fact, what I'd like you to do is to verify that you kind of followed along and try it on your own. take a minute and take this force and move it to the other side. So let's do the problem this way with our 10 newtons pulling on this side. You're going to have to make some changes to your free body diagram, but I think only in the horizontal directions. If you're trying to take notes and you want a good idea of what to do here, I would start a new problem, especially if the quiz wasn't great for you. But we'll start by realizing that the 5 kilogram car is experiencing 10 newtons to the side. Still a 50 Newton car. However, there's going to be a tension this way. And then the 15 kilogram car is going to have a Newton's third law of tension this way. And it's the only real change. I could skip a step and just treat it like one big box and say that it's, one big box of mass 20 kilograms. I could treat it that way. The only reason I'm treating it separately is I want people to see that, well, we've probably, if we want to know what's going on internally, we do have to break it up into pieces. But if you're trying to do this fast, you're trying to skip steps, you could probably just say, well, 10 newtons equals 20 kilograms times A. There's no reason you can't. You can treat it like one big object. But I'm going to do the whole problem the long way. 10 minus T equals MA. That's the first car. And T equals 15A. That's the second car. I'm going to pull this together. I'm going to add the two equations together. T's will cancel out. I'm going to add 5 and 15 together and get the same thing we had a minute ago. And show that the acceleration is still half a meter per second squared. So pulling on the other side doesn't change how fast the system goes. You're pulling with the same force. That part doesn't matter which car is first or second. But this part does. If I want to know what the tension is, well, I could pick one of these to plug it in. I'm just going to do it once. I'm not going to check my work this time. But I get tension equals 15 times 0.5, which is 7.5 newtons. Now this part is important to me. That if you're taking good notes, you want to add something that's important, the order matters. The heavier car needs more force to move it. The heavier car needs more force to move it. So if I pull on the light car, there's going to be more tension in the coupling here because the heavier car needs more force to move when compared to the lighter car. It's just the way it is. So the order matters. If you put the lighter car first, then you're going to put a lot more strain on the coupling. If you put the heavier car first, a lot less strain on the coupling. Also consider that in the last example, the coupling only had 2.5 newtons of tension in it. This time it's got not just a little more, it's got 3 times the amount. That means this is 3 times harder to do on that coupling by just changing the order of the cars. It also means that this little car, it's being pulled in 2 directions, just like we talked about a minute ago. But now, 10 newtons this way and 7.5 newtons that way. That's a lot more stress on that car. It could break. So when we look at the order matters. And it changes the dynamics of what's here. Now, you might not understand this, but some of you have probably played these kind of silly. So try this one out. It is almost a perfect simile to what you just did. Slight variation, but not really very much. Once you figure out the difference, you'll see that it's all going to be the same kind of thing. But find the acceleration of the system and the force between the boxes. Everybody's, I only got to see a few, but already I see that, maybe some of the lessons from the minute ago didn't sink. Let's talk about the 5 kilogram one. Yeah, 10 newtons this way, sure. And 50 this way, sure. And a normal force this way, probably 50. But it's in contact with this box. That's a surface. And because it's a surface, that's a normal force. So there has to be a normal force that is perpendicular to the surface, so there's a normal force this way. You're trying to push the box to the right, but the second box is trying to keep it from moving. It has inertia, so some of you miss that. The other box, yeah, 150 here. Normal force here, but it too is experiencing that same normal force. If you want to differentiate, we'll say normal force in the x direction, so we know which one we're talking about. That's the force between the boxes. Instead of there being a cable connecting the two boxes together, one box is directly pushing on the other. Still the same kind of thing, guys. Net force equals ma, so on this box, normal force equals 15a. On the other box, well, 10 minus normal force equals 5a. But this is the normal force in the x direction. These two normal forces have to be equal and opposite. They're a Newton's third law pair. Now, we did just do this exact same thing, didn't we? Just had t in there and not n, but it's the same kind of problem. If I bring this over to the other side, add them together, I'm going to get the same acceleration. It works out the same. Again, it'd be like if I took and put one big 20 kilogram box here. The pushing force doesn't know the difference. Boxes just slide based on how big the inertia of the system is. But if I want to figure out what that normal force is, I'd have to go back, plug it in here. When I do, I find that the normal force equals 7.5 newtons. The difference here is instead of the box being pulled apart, that little 5 kilogram box is experiencing 10 newtons from this side and 7.5 from this side. It's being crushed. You guys who have worked in like a store before and you're having to move boxes around, in this case, you push on the big box, put the little box out front. If you do it the other way, you're going to crush the little box. That's all that's going to happen. That was what will happen. This is also why things like if you are holding a heavy bag of groceries and you bang your hand into the door frame, well, your hand stops, but the rest of the package keeps going into your hand. Why it hurts more than if your hand doesn't have anything in it and you hit something like that. It's got to deal with the fact that there are two forces acting, one acting on one side and one acting on the other.